topic. Yeah, the topic is plasma expansion through magnetic nozzle and its applications, which we have been working for last few years. So I would like to start with. I like to start in our lab. First of all, our senior members, Professor Ashish Ganguly, Professor Aditare, they are currently has retired from here. However, the plasma lab, IIT Delhi, has been founded by them, the experimental plasma lab. And Professor Ramesh Narayan, and other members are there also, we have taken over them. Particularly, I am particularly for this work there. So, Dr. Anshu Verma, she was awarded already her doctoral degree. She mainly contributed for the thruster work, and Ms. Preeti Singh, Ms. Shweta Sharma, they are awaiting their PhD degree final years. So they contributed for the other work that I said that electron cooling and negative ion generation. And we also acknowledge and thanks our funding agencies who are DST and later it is the DST SIR, through which we got a project for the thruster, and for the second one, Institute of Plasma Research, and as well as, of course, IIT Delhi for a different infrastructure building. Yes, so I will describe our experiments here, but before that, I think it is better because of a common audience, I'll discuss that what is the plasma in general. Many of you must have idea about it, but still we can recollect few of the things there. So plasma in general, this is mentioned as a fourth state of matter. Because you can get like in other states, you can see the solids, liquids, and the gas. Solids, their bondings are very good, so therefore they actually stay together among themselves. And when you put energy, you have to heat it. So heat means that it is a kind of energy you are giving into the solid, and therefore their molecular bonds are there. Molecular bonds are there. That actually started to break apart or becomes weakened there. So therefore they becomes a little bit free, and that forms a liquid there. So in the natural state, like your room your environmental temperatures, you can understand that there are, like, for example, H2O, that our room temperature is 20 degree, 25 degree centigrade, that becomes naturally that can remain state as a water, right? When you cool it, then it becomes a ice there. So after that, as soon as you give more energy, so therefore the bond, the weak bond that was exist between these molecules, that also becomes more weaker, and it in fact actually breaks out there, and therefore it starts becoming, we say, individual molecules which is roaming around there. So that is a vector of the steam there, or in general, now comes the last part. What would happen that if you put more and more energy to the gas there? So therefore, you can see that as I show that reactions here. Here, this is we say that ionized gas means that the atoms or the molecules are that in fact dissociates there, or even from the molecules, like in this case of hydrogen there, that it breaks apart and it produces ions. So it could be, here we can show that H plus there, but it could be H2 plus also, and it generates, we call it electron ion pairs, which stay together, and this is called we call it as a plasma form. So you understand that we have given enough energy, so that system has enough energy, so it's a very energetic, high energy system that we call plasma. So here the oxygen also is also there, so oxygen also will form the ions and the electron pairs, which is not shown here. So, however, what happens that when we do experimentally, when we create plasma, that we generally use a kind particular gas for our ease of. Yeah. So, for example, H2 you give there, so there are different components actually stays together. One is you understand that electrons and the ions are that. And it not happens that all the gas particles, the gas molecule that becomes ionized. So therefore, they cause the neutral species also coexist. And as well as you, if you, I hope आपको सबको पता है that there are ground state में रहता है like molecules and these atoms they can atoms electronic ground state में रहता है तो वहाँ से excite you can also excite, right? So therefore that means that electrons can be go from this one shell to another shell there, but it doesn't come out from the atoms there. So it can actually different excited states also possible because okay it is it is actually high energy system, right? So that actually makes a plasma is a very rich system there. So which means you have a different type of species all together there. Therefore, it can be utilized. That's why it can have a different type of and various type of applications. Reactive species, we say reactive species, and that can be for a, especially like a material processing, etc. It works better. Solid to liquid, liquid to phase. These are called like what we call this phase transitions, right? So, and you understand that this plasma, you are putting the very high energy there. So, in our terrestrial, I mean, जो हमारे चावल मतलब इतना टेम्परेचर नहीं करता है. So therefore, otherwise we won't be able actually here. So, इसलिए plasma generally we don't see in and around. However, like stars, which is a really very hot system there. So they are like plasma actually exist very naturally, but not okay. We have to create it. If you in your lab we create it, or the other form of the plasma example is that, for example, big discharge happens there in that. During the lightning, so that you can, that is also a plasma. You can say that. Okay. So plasma that we have to, what is the characteristics of the plasma? So characteristics of plasma, it is characterized by one is that temperature. So as I said that you have there are different species are there. So the one is like a electrons, ions are there, and you have a neutrals are there. So electrons, they are very mobile, they are very light. So that's why they are very mobile there. So what happens that we have to give energy. From any source, you can give energy. That energy need to transfer to the gas. So electrons, in fact, actually, they take the energy and they become very hot there in general. There. And what happens that they don't maintain, they maintain their own distribution. And because they are very mobile, so they don't interact much with the ions also, ions and the neutrals. So therefore, they follow their own distribution function. So what happens is their temperature becomes different. तो प्लाज्मा की जब टेम्परेचर बोलते हैं तो हम लोग क्या करते हैं कि यहाँ पे एक इलेक्ट्रॉन का जो टी है ये इलेक्ट्रॉन का टेम्परेचर है और जो आई मतलब आयंस का मतलब है तो आयंस का अलग सा टेम्परेचर है और टेम्परेचर मतलब क्या है कि एनर्जी से जैसे टेम्परेचर हो जाए एवरेज एनर्जी कोई डिस्ट्रीब्यूशन फंक्शन आपको थोड़ा बहुत आई होप आपको पता है एवरेज जो निकालते हैं दैट एक्चुअली रिप्रेजेंट्स टेम्परेचर
हेलो सर
होता है मोशंस खूब ज्यादा होता है और आयंस तो हेवी होता है तो हेलो हेलो
sir, you can switch off your video na, it is taking much bandwidth.
Okay, I didn't realize that.
Yeah.
It's all right now.
Yeah.
ठीक है
Yeah.
टेम्परेचर होता है तो नॉन थर्मल प्लाज्मा हम लोग बोलते हैं कि टी in fact much higher than the ion temperature and ion temperature जो gas temperature मतलब आप जैसे कि जो रूम का टेम्परेचर है तो वो 20 ऐसे होगा तो केल्विन में हम लोग बोलते हैं 300 केल्विन लाइक दैट। और इसका जो होता है इलेक्ट्रॉन टेम्परेचर लैब प्लाज्मा इट कैन डिफरेंट है। सो हमारा जो जोन है यहाँ पर डिफरेंट टाइप ऑफ प्लाज्मा I have mentioned here. So what we work there in general that typically the charge particles per meter cube, so 10 to the power 15 to 16, that is the density, density or the particle charge density or number density, we say that. That means per meter cube में इतना number of ions per रहता है. तो temperature is there. If you say electron temperature generally 10,000 to 20 power 4 like that. हम लोग generally इतना ऐसे केल्विन से नहीं बोलते, but we say that electron volt. So near around 10,000 Kelvin, 10,000 Kelvin, or you see almost like 10,000 degrees centigrade. ठीक है, so it बहुत हाई टेम्परेचर है, बट आयंस इतना टेम्परेचर में नहीं रहता. इट कैन बी आयंस का भी क्या होता है अगर इंटरेक्ट करे, और तो जैसे कि फ्यूजन रिएक्टर में जैसे होता है कि दैट इट कैन बी दैट आयंस का टेम्परेचर इट कैन बी वेरी हाई. इट इज फॉर इट हाई टेम्परेचर की जरूरत है फ्यूजन वन बन जाता है. फ्यूजन में टू न्यूक्लियस दैट राइट. सो हमारा जो ऑलमोस्ट लाइक एज आई सेड हियर, एंड जो लैब में जो प्लाज्मा हम लोग बनाते हैं वो is greater than Ti. So जो भी हम बोलते हैं इलेक्ट्रॉन टेम्परेचर, अब that naturally comes that इतना high temperature आप generate कर रहे 10,000 degree centigrade something like that. तो इसमें क्या it can be ना इतना high temperature how to sustain all the things. कुछ कंटेनर में हम लोग प्लाज्मा बनाते हैं, we'll give the example. So the point is that it is the heat capacity. Electron का mass is very low, so therefore the heat capacity is also very low. So that doesn't matter. Ions का अगर होगा तो problem होगा. Ions का also एक कोई गैस में ions are the one और प्लाज्मा में that they carry most of the mass there. Right. Other is that it maintains quasi-neutrality, so our plasma that overall neutral. Even there is a charged particles are there, but it's an overall neutral. So it means that electron density is almost equal to the ion density. And these are the two other things which is whenever we define plasma, this is called the Debye length. Lambda d that is defined by the constant there, and it relates the temperature of the plasma. So electron Debye length is electron T, and N is also same there. So this actually gives that some idea that plasma, it is like in your conductor, right? You know that agar koi conducting metal, so that electric field cannot penetrate that, right? Here also plasma, it has like both type of charged particles are there, so electric field in general cannot penetrate to the plasma. So unless it is there is some certain with the AC electric field, some certain frequency, otherwise it cannot penetrate there. And this actually gives you that that what is that if somehow there is electric field is generated, it immediately shielded. So that shielding length actually almost it is a true Debye length. It is characterized by the Debye length. Okay. And plasma frequency is a naturally is there because you see that electrons and ions, they are roam free. They are like as a free body, they are roaming around here and there. So, but the point that if, but we say that it's a quasi-neutral. That means it's in any smaller volume like that. So, number of charged particles, negative charge particles should be equal to number of positive charge particles. So, somehow if you can try to say separate out, that means the negative means that just Yeah, can you hear me clearly now?
Yes, sir.
Okay, okay. Fine. Let me share. You can see my screen?
Yeah, yeah.
Okay. Okay, fine. So plasma frequency, as I was saying, one is like that it gives that lambda d, which is called a Debye length. It gives that the shielding, any electric field that is generated, it tries to shield that. And plasma frequency is that this is the natural oscillations of the plasma whenever some kind of, say that because it has the two types of charge particles carriers there. So like this, it is try to it is called a temporal shielding in fact there. So because if suddenly some electric field is there, so therefore that we in which time scale, so 1 by omega p gives the time scale. At that time scale it can reduce that any type of electric field which is generated inside the plasma disturbance. Okay. Fine. So there are, as I said, there are different type of discharge mechanism. We have a lab in the laboratory. We generate the plasma. So these are some of the example I have shown here, which are very common examples. Like one is first one is a directly coupled discharge system that we can see that there are two electrodes are there. Two electrodes are there here, and one is negative and one is positive there. So if you put like a high voltage there, and there are some stray electrons are there, and this electron, because of this high electric field is generated, there is a current start passing through them, and the electrons get energized first, and they uh, after high energy they collide with the ions. I collide with the neutrons and therefore produce more electrons, and this is how the discharge takes place there. So these ions, you can understand, it goes to the negative part, the cathode part, and there are secondary emissions, electron emission emitted also, and this electron goes to the anode at a discharge. So the current passes through, which is called as a discharge current there. Okay. So other part is like instead of here is a static DC bias. What you can do, you can use some AC voltage there. So this one is, so I see that pure AC voltage. Any type of DC, we are blocking it here, which is applied between two electrodes there. So it is called the capacitive. So this plasma also, you can understand, it forms like one capacitance there. And this forms we call the capacitively coupled discharge system there. So these systems are very popular for different type of material processing there. So, and the frequency that we generally that applied is like in RF or radio frequency in megahertz there. This one is called here again this RF system is voltage is applied. This discharge, sorry, RF voltage is applied here. We call it inductively coupled discharge system. We call it an inductively coupled discharge system. So there is a this is someone is actually fine. So there is oscillating current actually flows through there, which is when the current is goes through this wire, it is wrapping around. This wrapping around is a piece of call it a coil, and this can be outside, this can be inside also. So when there this current passes through there, this produces you understand, you know, right? There is a magnetic field will be produced there. So magnetic field, when it is an oscillating current, AC current, so therefore the magnetic field is also changed there. So changing magnetic field, that also produces electric fields, and that electric field, like what is working here, that electric field accelerate ions there, and it generally energize the ions after that take care to clear the plasma. Okay. So here it is like a microwave, we saw the microwave ECR discharge system. This one in the megahertz range, and this one is like a gigahertz range. Gigahertz means that 10 to the power 9 hertz. So here in that case, we directly, we call it a microwave. So that microwave that goes into the gas directly. So there are systems are there to couple it there. And generally, typically, we use a 2.45 gigahertz, which is a like industry standard to use the 2.45 gigahertz. And we call it a ECR. It is called the electron cyclotron resonance discharge. If you see that, there is a magnets are there. This is magnet coils are there, which is generate a magnetic field there. And this magnetic field, the magnetic field, when the charge particle, they actually rotates around the magnetic field. And that rotates with a certain frequency, which we call the Larmor frequency, gyration frequency there. So this 2.45 gigahertz that we create a suitable magnetic field so that the gyration frequency that becomes equal to that angular frequency of this incoming wave. And when that happens, that that frequency, when the frequency matches, there is a resonance effect. So therefore, that wave carries some energy, and that energy transfers to the collisionless to the electrons. Okay, and the electrons becomes highly energized there, and it creates because the energy becomes too high here, and that we can get again electrons need to energize, and after that with the other collision it can create plasma, right? This electron ECR actually it is a very efficient system for power coupling, especially at a low pressure. So our work, in fact, it actually deals with the ECR. So we have other type of systems also, but this work that I will explain here, it relies on the ECR discharge there. Okay, so ECR discharge, as you can see in the last slide, here the waves actually comes there and the plasma actually produce. Here at some zone actually, here near to that, there is a plasma is produced there. Here you can see that it is showing ECR discharge there, where there is an appropriate magnetic field is there. Right. So now we produce that plasma in some small volume here. Okay. It has to be small volume around that 2.45 gigahertz. That means if you do that, try to see what is the wavelength. The wavelength comes around like 30 centimeter there. So the plasma system also has to be the dimension of the system nearly like that, right? 10 centimeter. So we create the plasma there, and after that, creating the plasma, we allow it to expand into a bigger volume. What we saw that this is the highlight of this work that you can expand it to a different volume, smaller to that large volume. So large means that expansion ratio that you can control it, right? And when you do that, what we saw that of course when it's expansion is there, it leads to the decrease in the electron temperature. Because when the plasma, creating the plasma, you need a really high electron temperature there. But after that, when you would like to utilize it for different applications, therefore you need some, depends upon the application, you need that electron temperature to be reduced there. Right, it remains in the very degree centigrade. You see, it remains in a very high temperature. But what is when the plasma where it is generated, at least you want to have it cool down there. As well as when it comes out from this chamber, therefore what happens that you get ions accelerated. You understand that? I saw that we work in our work is a non-thermal plasma, which means that the temperature of the electron is very higher than the temperature of the ions. So ions का temperature कम है मतलब कि इसका motion मतलब thermal motion वो भी कम होगा, उसका velocity thermal velocity will be low, it will be lower actually. However, if you allow it to expanding, therefore what it's seen that the ions can be accelerated very high value. So it has its different applications that I will discuss here. Okay. Okay, so I will now go to our experiments I will try to explain it in as easy as possible way, right? ठीक है. सो जैसे कि हाँ, प्लाज्मा हम लोगों ने बनाया इलेक्ट्रॉन साइक्लोट्रॉन, ईसीआर डिस्चार्ज हम लोगों ने यूज किया है. और दिस वन इज लाइक वी सेड दैट कॉम्पैक्ट इलेक्ट्रॉन साइक्लोट्रॉन रेजोनेंस source. So it is a so C and just ECR का E and plasma I have missed here. So P and S. So we call it CPS actually. So compact electron cyclotron resonance plasma source, right? So that उसका जो वॉल्यूम है, I have not mentioned here, the diameter is around 9 centimeter and the height, that length is around 15 centimeter, like that, right? And your expansion chamber that we have said, so expansion chamber, like for expanding, it is expanding to a very high chamber. So expansion chamber, we have used two expansion chamber. One is like that cylindrical system. One is diameter is 50 centimeter, length is 70 centimeter. Another is very large system, like 1 meter, length 1 meter. So you can see almost like it's completely diameter wise that is double over here. Yeah. So, and we had utilized two gases. One is argon gas, another is hydrogen gas. और जब प्लाज्मा है तो प्लाज्मा का डायग्नोस्टिक्स करना पड़ेगा, तो प्लाज्मा कैरेक्टराइजेशन करना पड़ेगा. तो प्लाज्मा का कैरेक्टराइजेशन, इफ यू रिमेंबर आई मेंशन दैट टेम्परेचर वो निकालना पड़ेगा, प्लाज्मा का डेंसिटी निकालना पड़ेगा. So therefore, and यहाँ पर जो होगा आयन का तो दो मोशन भी है. So this is a mistake, some typo is here. We said that returning field ion energy analyzer, उससे हम लोग क्या करते हैं, आयन का एनर्जी मेजर करते हैं. ठीक है. So आयन का वेलोसिटी that can be measured. हाँ, तो यहाँ पर जैसे we see that compact ECR plasma source, the CEPS that I mentioned here. So this one is the schematic diagram of the CEPS. You can see that we have to we use microwave. Microwave at 2.45 gigahertz. So exactly 2.45 gigahertz. That is what used in your microwave oven. जो food heating के लिए हम लोग use करते हैं. That is what it is here. But in industrial scale में है तो इसका power you can make it a very high there. So otherwise that magnetron जो बोलते हैं coil वो same वहाँ पर ही रहते हैं. ठीक है. तो ये जो होता है ये होता है वेव गाइड. सो माइक्रोवेव है, वेव्स डायरेक्ट हम लोग वेव गाइड से इसको पास कराते हैं फिर इनसाइड द सिस्टम पे. पर हमारा जो एक्सपेंशन चेंबर और ये कैन सी दैट एक्सपेंशन चेंबर दैट इज अटैच्ड टू दिस सोर्स. ये वाला जो है सोर्स. और क्या है जो बताया था, एक मैग्नेटिक फील्ड भी चाहिए. तो मैग्नेटिक फील्ड है, यू कैन सी दैट दीस आर कॉल्ड एक्चुअली रिंग मैग्नेट्स. तो एक बड़ा बड़ा रिंग है, वो रिंग तीनों रिंग मैग्नेट्स को एक साथ लगा दिया है हमको ना. और इससे जो कहते हैं रिक्वायर्ड जो मैग्नेटिक फील्ड है दैट वी get it from this ring magnets. Fine. So that a little bit of this one, that this figure that can give you some idea that जब field करते हैं magnetic field करते हैं तो these are the called what are the field lines. So these are the called magnetic field lines. Is that if you say any magnetic pole which will follow that field lines. ठीक है. और जो 2.45 गीगाहर्ट्ज के लिए हमें जो चाहिए 875 गॉस चाहिए. सो 875 गॉस दैट दिस रेड लाइन यहाँ पर जो ये फील्ड लाइन होता है, इन टू लाइंस हो यहाँ पर 875 जो गॉस मैग्नेटिक फील्ड प्रोड्यूस हो रहा है. और यहाँ से जो होता है यू कैन सी दैट ये वाला जो है मैग्नेट्स जो है एक हाफ हम लोगों ने दिखाया. जैसे कि इसको आप अगर कट कर दीजिए, इसको एक जैसे इफ यू कैन कट इट लाइक दैट देन व्हाट यू सी इट इज द डायग्राम, टू डायमेंशनल डायग्राम हम लोग दिखा रहे हैं यहाँ पर. सो माइक्रोवेव यहाँ से आता है यहाँ पर. और क्या होता है कि यहाँ ये दिस पार्ट एक्चुअली इट रिमेन्स इन द एटमॉस्फेयर, राइट, एटमॉस्फेरिक प्रेशर. और यहाँ पर जो होता है कि यू कैन सी दैट दिस ब्लू वन ये वैक्यूम सील्ड क्वार्ट्ज प्लेट है. ठीक है, क्वार्ट्ज प्लेट है, क्वार्ट्ज से माइक्रोवेव अंदर चला जाता है. यू कैन नो दैट अगर अनलेस इट इज ए कोई मेटालिक बॉडी ना हो तो कोई इंसुलेटर से ऑलमोस्ट माइक्रोवेव एक्चुअली पास कर जाता है. दैट्स व्हाई योर फूड आल्सो गेट हीटेड, राइट. सो क्वार्ट्ज प्लेट से क्या होता है, इट कैन गो टू द हियर द गैस इज हियर. यहाँ से पहले यहाँ पर प्लाज्मा बनता है फिर एक्सपैंड करते हैं. एक्सपेंशन चैम्बर हम लोगों ने बताया है, एक्सपैंड करते हैं. ठीक है. तो ये जो पोर्शन है यहाँ पर ही मोस्टली प्लाज्मा बनता है और कहीं पर नहीं बनता है, यहाँ पर प्लाज्मा बन जाते हैं एंड आफ्टर दैट इट passes. You can see that here this field lines जो होता है, field lines जो होता है ये this is called the magnetic field lines, जहाँ पर you can see the field lines are very nearby, near basically closely spaced है. जब closely spaced होता है field lines तो इसका मतलब है कि the field is very high है. और जब यहाँ पर you can see it is actually diverging, जैसे कि इसका spacing are becoming very high है, so therefore it is diverging. Diverging में मतलब इसका field actually down हो गया. तो ये जो होता है कन्वर्जिंग टू डाइवर्जिंग जो फील्ड होता है इसको बोलते हैं हम लोग मैग्नेटिक. ओके एंड दैट एक्चुअली दैट गिव्स यू द आइडिया दैट दिस इज द मैग्नेटिक, वी कॉल दिस अ नोजल. हेलो हेलो.
Yes, sir. Sorry,
you can hear me, right? You can hear me.
The voice is not coming properly.
Oh, probably network there is some problem here. So because I also cannot hear, it's a broken. Today it is very rainy here, so that could be one reason there. Otherwise, it perfectly works there. This system. So, hello, it is clear now. Hello.
Yes, sir. Yes, sir. But it's better to speak slowly.
Okay, okay. Your voice is also not clear now. That is also, I actually changed that network. That's why mobile, our IIT network to mobile network I changed here. So I thought it would be better a little bit. Okay, so yeah, let us continue. What can we do? Right now I don't have anything else there. So let us continue there. Probably you can see. Okay. So yeah, so this is the field line, as I said, so that's why it is called the magnetic nozzle here. And this one, you can see it is we call it a CPS here, and it's a very compact system you can know. And this is one of the earlier old system we had for different type of processing here. So here you can attach multiple CPS, and that can produce plasma, and it can go and fill up the chamber. Okay. Yes. So the first one I explain here, the CPS which is attached to the medium volume plasma system here. So you can see this is our experimental. This is the experimental setup here. So that this plasma source is attached here. Plasma is produced, and it expands to this this expansion chamber. There is a magnetic nozzle here, but I have not shown the magnetic lines, that you have to understand. This is a real picture of this system here. Okay. Then you see that. Yeah, just a minute. Yeah, Dr. Shintu, is my voice is actually, you cannot hear it, or it is completely gone, actually, completely broken?
How is clear?
It is clear. Otherwise, I will. I mean, it is okay, right? Right now, it is okay.
Yeah.
Okay, okay, okay. Otherwise, what I can use my laptop. That can be another option there. Because okay. All right. So yes. Right. So, but that what I was explaining, it can show you much in a better way that these are the lines inside the source here, and here the plasma is produced. And what you can see that when I plot this field along the axis, you can see that here the field is very high, which represent that where that converging part was there. You remember, here the converging part is there. Right, and after that field is down as a central, that it is a diverging. So this type of, whenever this type of profile you see, this is called the magnetic nozzle here. Because of the ring magnet, the field structure is a very complex inside there, which I am not explaining here. It is not also purpose for this talk there. But as I said, this is the magnetic nozzle there. So what happens that one of the advantage of the magnetic nozzle is there, that whatever the plasma it is inside, because the plasma that you understand the electrons, ions, they can actually rotate along the field. So it can actually confine the plasma. It can confine the plasma inside the magnetic field, and also it can just take it out. So which means that expansion by electron, when it is inside the plasma pressure, you understand that the charge particle that is high, so it is that it will try to diffuse outside, flow outside there. But here the thing is that it can also aid in to come out from the system. That is what we want. Yeah. So you may not whenever we actually characterize our plasma by this, that measurement is done by, if you see it here, we call it the Langmuir probe, or utilize different type of Langmuir probe. So this Langmuir probe here, it is just like a point, it's a kind of wire that goes there, and from where actually we apply some bias, and it can measure what is the current it is drawing there. And with this current drawing, that we can analyze it and find out that what is the plasma electron temperature and the plasma density. These two we can find it out with the Langmuir probe. And whenever this there, we need to see any experiment that we need to probe, right? So therefore, any properties we need to see. So that is why Langmuir probes are used here. See it here that we have measured axially the plasma density. Axially plasma density. So the plasma density, 0 means that 0 means here Z along the Z. So therefore 0 means here inside the plasma is very hot. So we couldn't probe much inside the chamber. So therefore the probe, what happens, it draws so much current, it actually the ohmic heating happens that it just burns out. Ekdam jal jata hai matlab. So we have suffered a lot. So we burned the probe and not used. So mostly we have limited our experiment measurement outside here. Okay. So density, if you see that, this is the plasma density. और क्या है, हम लोगों ने दो pressure maintain किया है inside the chamber. It is, we maintained it very low, 0.3 millitorr, 0.5 millitorr. बहुत high pressure होगा तो ECR जो है वो काम नहीं करता. So you understand that it is so low pressure. हमारा जो atmospheric pressure है, that is 760 torr. And you can see that it is a 0.3, not only torr, it is a millitorr. Means 0.3 into 10 to the power minus 3, which is 3 into 10 to the power minus 4 torr. It is a very, very less there. So what we do generally, whenever these systems are there, there is a pump is attached here. There is two-stage pump is attached. So we evacuate the system. इससे पंप चालू कर देते हैं, इसको पूरा evacuate कर देते हैं, so that means atmosphere, मतलब जो नाइट्रोजन ऑक्सीजन जो एयर है, एयर completely निकल जाता है. Completely मतलब कि इसका 10 to the power minus 6 torr में चला जाता है. So मतलब 760 torr, 1000 torr, उससे मतलब 10 to the power 6 में चला जाता है. And after that we allow some gas to fill in. कुछ गैस में हम एक्सपेरिमेंट करते हैं तो प्योर गैस. So इसके लिए हम लोगों ने जो यूज किया है आर्गन गैस. तो आर्गन गैस में हम लोगों ने एक्सपेरिमेंट किया. तो उसके बाद प्लाज्मा बनाते हैं और प्लाज्मा देखते हैं कि कैसे है आर्गन प्लाज्मा. तो आयंस मतलब आर्गन प्लस होता है और इलेक्ट्रॉन्स तो इलेक्ट्रॉन्स ही सिंगली चार्ज होता है. तो यहाँ पर जो है प्लाज्मा डेंसिटी. सो प्लाज्मा डेंसिटी, यू अंडरस्टैंड दैट सोर्स के यहाँ पर इट्स अ वेरी हाई. यहाँ मतलब जो मिलता है इट इज अ वेरी हाई. एंड आफ्टर दैट हम लोग मेजर कर रहे हैं. एक्सपैंड हो रहा है, मतलब एक्सपैंड हो रहा है तो बाहर की तरफ, तो इसका डेंसिटी भी कम हो रहा है. डेंसिटी भी कम हो रहा है. Or you can see the electron temperature also. Electron temperature inside the plasma, it is a 20, it is near, not like in the plasma also, very near to the plasma, so 0. और यहाँ पर थोड़ा अंदर गया है, तो it is a 20, or even actually we got a very high, even more than 20 electron volt we got sometimes. And that actually cools down. As it comes out, density भी कम हो जाता है और ये भी कम हो जाता है. ठीक है. प्लाज्मा पोटेंशियल जो है, प्लाज्मा का मेंटेन करते हैं पोटेंशियल. तो अभी may not be this is not be there, but what you see that ये पोटेंशियल जो होता है, पोटेंशियल कुछ जीरो पोटेंशियल के रेफरेंस में हम लोग लेते हैं. तो प्लाज्मा के ये हाई पोटेंशियल में मेंटेन करते हैं. और you see that when this also remains, ये क्या होता है, प्लाज्मा पोटेंशियल almost like it follows the electron temperature. तो ये हाई पोटेंशियल है, ये लो पोटेंशियल है. तो ये क्या होगा कि हाई पोटेंशियल से लो पोटेंशियल मतलब क्या होगा, यहाँ पर एक पोटेंशियल का ग्रेडियंट होता है, और यू नो रहता है इलेक्ट्रिक फील्ड क्या होता है, इलेक्ट्रिक फील्ड होता है कि ग्रेडियंट ऑफ द पोटेंशियल, उसके ऊपर डिपेंड करता है, राइट। सो दैट E इक्वल टू माइनस, राइट, द इलेक्ट्रिक फील्ड जो होता है, राइट, अगर वेक्टर जो होता है तो माइनस डी वी बाई डी आर, राइट, और dx यहाँ पर अगर होता है तो dz हो गया सर यहाँ पर, ठीक है। तो हमारे इलेक्ट्रिक फील्ड सेटअप हो रहा है, हाँ इलेक्ट्रिक फील्ड क्या सेटअप है, पॉजिटिव टू नेगेटिव मतलब, हाँ तो ये क्या होगा कि आयंस को एक, इट विल अट्रैक्ट द आयंस देयर, हाँ पॉजिटिव टू नेगेटिव, नेगेटिव की तरफ आयंस अट्रैक्ट होगा, दिस वन इन फैक्ट एक्चुअली, this one in fact helps to accelerate the ions there, हाँ तो आयंस को एक एक्स्ट्रा मतलब एक्सपैंड हो रहा है, एक वेलोसिटी दे रहा है, हाँ तो और क्या होता है, नोजल क्या हो गया, तो नोजल की वजह से क्या होता है कि नोजल एक्चुअली इसको एक डायरेक्शन देता है, हाँ जैसे कि प्लाज्मा को कंफाइन करता है, हाँ मैग्नेटिक फील्ड में जब होता है कि प्लाज्मा वहां पर ऐसे स्टिक हो जाता है पूरा, हाँ ना उसको एक डायरेक्शन बाहर की तरफ भेज रहा है मतलब, तो यहाँ पर इसीलिए क्या होता है कि यू गेट ए लाइक ए डायरेक्टेड आयन एक्सेलरेशन टुवर्ड्स द जेड एक्सिस, ठीक है, ठीक है। सो there this is the some radial measurement also we do with this probe, these are the probes at the radial measurement, and you can see that what it shows here, that as you progress at different 13.8 centimeter near to the source and 38 मतलब काफी far away from the source, और ये क्या दिखाता है कि यूनिफॉर्मिटी मेंटेन करना है, रेडियल यूनिफॉर्मिटी ज्यादा हो रही है। यहाँ पर देखिए इसका जो होता है कि ये जो डेंसिटी डिफरेंस मतलब रेडियली, तो हम लोग ये मेजर करें ऐसे, इधर से यहाँ मेजर कर रहे, रेडियल यूनिफॉर्मिटी एक मेजर किया यहाँ पर, एक मेजर के थोड़ा दूर में, तो रेडियल यूनिफॉर्मिटी एक्चुअली इंक्रीजेस एज यू गो बैक, थोड़ा और रिजल्ट हम लोगों ने देखा है नहीं यहाँ पर, बट इफ यू गो अनदर लिटिल फार अवे, ये ऑलमोस्ट लाइक ए फ्लैट प्रोफाइल हो जाता है, हाँ ये जैसे इट्स नॉट अ फ्लैट प्रोफाइल, इट इज लाइक ए डिक्रीजिंग है, बट वो ऑलमोस्ट फ्लैट प्रोफाइल हो जाता है, कि इसका यूनिफॉर्म एक पूरा रेडियली क्रॉस सेक्शन में यूनिफॉर्म प्लाज्मा बना है, जिसका डिफरेंट टाइप ऑफ एप्लीकेशंस, ठीक है। और जैसे हम लोगों ने बताया कि आयन एनर्जी, सो दैट मींस एक वेलोसिटी मिलता है कि तो हाफ एमवी स्क्वायर इज अ काइनेटिक एनर्जी, दैट वी नो दैट, ठीक है। तो आयंस का वेलोसिटी मेजर करने के लिए इसको बोलते हैं रिटार्डिंग फील्ड एनर्जी एनालाइजर, तो इससे क्या करता है कि कैसे इससे ग्रिड, जैसे कि जाली है मतलब, देयर आर दिस डिफरेंट टाइप ऑफ फिल्टर्स वी यूज देयर, तो पहला वाला जो यहाँ पर 4 ग्रिड्स है, और तो द फर्स्ट वन एक्चुअली रिपेल्स द ऑल द इलेक्ट्रॉन्स, इतना हाई वोल्टेज देता है कि नो इलेक्ट्रॉन्स कैन पास थ्रू देयर, एंड आफ्टर दैट क्या करते हैं कि आयंस मतलब आ रहा है मतलब, सो आयंस जब से आता है, एक और एक ग्रिड है जब वी हैव मेंशन हियर, सो देन आयंस व्हेन इट कम्स देयर, देन आयंस अपने वेलोसिटी से आ रहा है, तो इसको क्या करते हैं कि हम लोग थोड़ा रिपेलिंग करना शुरू करते हैं और रिटार्डिंग करना शुरू कर देते हैं, कि अगर माइनस थोड़ा वोल्टेज दे इसमें कि आयंस को रिपेल करना शुरू कर देगा, और जितना आयंस का हाई एनर्जी है वो ओनली कैन पास थ्रू दैट, सो दैट वी कैन सी द करंट, यू कैन सी दैट जब तक आप मतलब इतने से वोल्टेज यू आर अप्लाइंग, माइनस से शुरू किया है, तो देन आफ्टर दैट व्हेन यू आर अप्लाइंग दिस वोल्टेज एज ज्यादा माइनस मतलब तो ये हो गया मतलब इट कैन अट्रैक्ट, इट इज नॉट अ प्रॉब्लम विद द आयंस दैट, बट जितना पॉजिटिव आप देंगे then you can see that the current actually decreases there, so which means that कि इसका एनर्जी काफी इतना तक एनर्जी इसका है, आयन का जो बीम है वो निकाल रहा है इसका एनर्जी, so वहां से हम लोग क्या करते हैं कि that we can find out कि आयंस का एनर्जी कितना है, that is the way we found it. That is the, I mean, take home message is that we find out that the ions का कितना velocity एक gain कर, that is the retarding ion energy analysis. And this is something like that. I think it may be not in this scope we cannot discuss yet. But we did some equation. One thing is that this is a very common equation. So if you would like to pursue, some of you may want to pursue PhD in plasma physics later. So this is a very elementary way to find out that what is the plasma density and the temperature when you give some certain power and what is the pressure. so these are some balance equation we used. So which means that कि अगर इतना इतना गैस मॉलिक्यूल्स था तो वहां से कुछ आपका बन गया, कुछ आयंस बन गया, मतलब तो वहां पर कितना बैलेंसिंग हो रहा है, कितना जो मॉलिक्यूल्स था वो कितना आयंस में बन गया, तो उसका एक बैलेंसिंग इक्वेशन करते हैं। और एनर्जी बैलेंस इक्वेशन मींस दैट कि आपने इतना पावर दिया, वो पावर कहाँ लॉस किया। तो अभी इसको डिस्कस करना मुश्किल है, but the point is जो है again I just give you the what why we do this, because हम लोगों को देखना पड़ता है कि कितना and you can see that कितना प्लाज्मा डेंसिटी है, कितना टेम्परेचर, ठीक है। और वहां से क्या होगा, यू कैन मैच विद योर एक्सपेरिमेंटल रिजल्ट। ठीक है, तो व्हाट वी डिड हियर, व्हाट इज द नोवेल्टी ऑफ दिस वर्क इज दैट कि हम लोगों ने इस दोनों को दो चेंबर में जो किया है, व्हिच हैज नॉट बीन डन बिफोर। सो इसको जैसे कि दो चेंबर में जोन 1 जोन 2, अंडरस्टैंड, दिस इज द कॉम्पैक्ट वन, दिस इज द एक्सपेंडिंग। तो यहाँ से हम लोगों के निकाल के हम लोग कहेंगे थियोरेटिकली यू कैन फाइंड आउट कितना प्लाज्मा पोटेंशियल बन रहा है, यहाँ पर प्लाज्मा पोटेंशियल, यहाँ पर प्लाज्मा पोटेंशियल, और उसका जो है कि जो डिफरेंस है हम लोग निकाल सकते हैं कि क्या कितना आयन का एनर्जी कितना हो सकता है। और हम लोगों ने देखा इट इज गुड, एक्चुअली गुड इनफ द एक्सपेरिमेंट। कभी हम लोग कोई एक्सपेरिमेंट करते, इट इज ऑलवेज बेटर कि ऑलवेज एक सपोर्टिंग थ्योरी हमेशा होना चाहिए। तो आप लोग कोई अगर कुछ भी किसी में एक्सपेरिमेंट अगर परस्यू करते हैं, दैट इज ऑलवेज better to do that. So one the point is that what we saw that when we do this, that this is called that the energy हम लोगों ने निकाला है। और एनर्जी से what you can find out, this is called the thrust actually। तो what is the thrust और कितना निकल रहे हैं, so n mu square और a मतलब जो है that is the area of this one। so वहां से कितना, बिकॉज इससे कम्स आउट है, so कितना फोर्स से बाहर आ रहा है उसको बोलते हैं थ्रस्ट। so that is the 56 millimeter we have found it out। or that also from the measurement at the model as well as from the measurement of this retarding pin energy analyzer also shows that around that also we are getting। so now इसका क्या applications, applications now let me show that what we are proposing, it is called the plasma thruster। so plasma thruster means that जो ions क्या होता है, ions are coming out from the that system, जो छोटा वाला compact system बोला है, ions are coming out, there are ions are one which is actually taking the mass, right। so एक mass मतलब अगर it comes out from that from the system, so एक recoil भी होगा फिर, है ना। कोई एक बुलेट अगर कोई गन से निकालते तो बुलेट निकाल जाते, फिर ये आ जाते। so that is we call actually thrust generation। so जैसे this is utilized in the rockets। so आपका कोई अगर rockets see that rockets देखो, missile whatever you check here that, तो यहाँ पर अर्थ में क्या करते हैं, अर्थ में यहाँ पर रहता है, तो वहां से कहते हैं हम लोग उसमें कुछ फ्यूल्स डालते हैं, कोई लिक्विड फ्यूल डालते हैं, उसको आप अगर इग्नाइट करो तो वो एक्सपैंड कर जाते हैं और बाहर की तरफ निकालते हैं। तो बाहर की तरफ निकालते हैं तो क्या होगा, जो ग्राउंड में वो क्या नॉर्मल फोर्स डालते हैं और वो उल्टा फोर्स डालेगा फिर। और वहां से जो फोर्स आएगा दैट इज द थ्रस्ट, और वहां से रॉकेट एक्चुअली गोज इनटू द एयर, राइट, दैट इज द थ्रस्ट। सो ये जो थ्रस्ट यहाँ पर ग्राउंड से अगर ग्रेविटी रहता है तो यू हैव टू मेक ए ह्यूज थ्रस्ट देयर। द थ्रस्ट दैट इज लाइक मोर देन लाइक 1000 न्यूटन और समथिंग लाइक दैट, Newton force, right। so that we have to produce so that it can goes out from the Earth's gravity। however this is not the case when you go to the space में तो gravity नहीं है वहां पर। तो वहां पर क्या होता है, you need two things are there। one is that we need a little medium type of thrust। क्यों, बिकॉज क्या होता है कि ऑर्बिटल करेक्शन होता है, देन यू हैव टू मैन्यूवर इट, मतलब यू हैव टू लिटिल बिट यू हैव टू मूव दिस। वहां पर मूव करने के लिए कुछ है नहीं, मतलब तो उसको जो मूव करना है और कुछ मैन्यूवर करना है, तो इसके लिए छोटा छोटा थ्रस्टर यू कैन यूटिलाइज इट, right, and that can produce some medium type of thrust like ये जो होता है कि 1 to 100 milliNewton type of thrust है, जो you can see हम लोगों ने अभी दिखाया कि वो आयंस मतलब निकल रहा है, which means that it can give it can utilize as a thruster there, which is called is like a space thruster। so space thruster there। दूसरा है कि to analyze it, वहां पर जो it has the plasma thruster का जो है, इसका जो propellant consumption is very low there। so जब मतलब डीप स्पेस प्रोपल्शन के लिए ये बहुत आइडियल होता है। अब डीप स्पेस में क्या होगा, डीप स्पेस में वहां पर तो ग्रेविटी नहीं, वेट नहीं है, यहाँ मतलब क्या आपको बहुत हाई थ्रस्ट देना पड़ेगा। बट अगर वहां पर थ्रस्ट उसका थ्रस्ट रेट इज गोइंग, इट कैन हैव ए वेरी हाई वेलोसिटी देयर। हाँ, तो उसको वही चाहिए ना, स्पेस में तो कोई ऐसे कुछ है नहीं, देयर इज नो वेट इज देयर, so it can do that. Or that point is that it can actually use a very low propellant and can acquire high velocity. Thrust is low, thrust is where okay, you have to make it no problem there. So that it come, you don't have to carry that much propellant. That is the thing. So आपका payload कम हो जाएगा फिर आपका. So therefore, it's called this a specific impulse is a very high for the plasma thrust. So it is utilized actually. It is utilized. These are the something. We don't go to the details. It is called the ion thruster and the Hall thruster. These are the very utilized for this purpose. there. Deep space propulsion के लिए क्या करते हैं फिर फिर जो मैन्युफैक्चरिंग जो बताया वो उसके लिए सैटेलाइट के लिए ये सब ऑर्बिटल सैटेलाइट्स ऑर्बिटल मोशंस के लिए ये सब यूज करते हैं. It has the current technology has some problem. One is like that it has to use electric. Different type of this electric. You can see this is a grids actually. Ions को क्या करना पड़ता है, एक्सीलरेट करना पड़ता है. आयंस को एक्सीलरेट करने के लिए क्या करना पड़ता है आपको, उसको you have to make it like some you have to accelerate with some electric field, right? So therefore you use some grids there. तो वो एक तो आपको एक्स्ट्रा ये करना पड़ता है. दूसरा आयंस जब it leaves only आयंस यहाँ से you are taking it out. So ions जब you are taking it out, तब क्या होता है कि इलेक्ट्रॉन यहाँ पर रह जाता है, वहां पर कहाँ जाएगा, स्पेस में कहाँ जाएगा वो, कोई ग्राउंड तो है नहीं. So it becomes actually, hello,
Yes, can you hear me?
okay. So this becomes energized. It becomes energized. So therefore that becomes a like a, it becomes a energized, which is a problem. You cannot bias it. So therefore इसके लिए न्यूट्रलाइज यूज करना पड़ता है. और तो न्यूट्रलाइज होता है, ये इलेक्ट्रॉन एक्स्ट्रा छोड़ता है, फिर जो आयंस को क्या होगा कि यहाँ से एक्स्ट्रा आयंस जाकर यहाँ से न्यूट्रलाइज कर लेते हैं. तो ये सब का एक्स्ट्रा यूज करना पड़ता है. वी हैव टू यूज. सो हमारा जो जो अभी जो थ्रस्टर वी आर एक्चुअली गेटिंग, तो यहाँ पर जैसे पूरा प्लाज्मा ही निकालता है, बाय द प्लाज्मा इटसेल्फ, मतलब आयंस एक्सीलरेट करता है बट उसके साथ इलेक्ट्रॉन भी निकल जाता है. सो ये वो सिंपल सिस्टम इट इज देयर. So but still it is in the experimental stage. Different groups are here. This is one case is called helicon thruster. Helicon means helicon is different way. I have not discussed there that it's another way of generating plasma. So that plasma is generated there and it expands there. So but in total क्या होगा, कोई आपको देखिए ये इसको बोलते हैं न्यूट्रलाइजर. और लोग कहते हैं न्यूट्रलाइजर. Another is like we don't have any power supply. सब यूज करने के कम हो जाए. ठीक है, हेलिकॉन में काम हो चुका है, बट हम लोग जो कर रहे हैं तो ईसीआर में काम कर रहे हैं. ठीक है, सो देयर इज अनदर ग्रुप एट फ्रांस, दे आर आल्सो वर्किंग, बट देयर सिस्टम इज लिटिल डिफरेंट देयर. और जो है कि हमारा थ्रस्ट जो कैसे है, वी हैव गॉट ऑलमोस्ट about that, and these are the other groups what they are utilizing there. This is like a right now it's almost like a 10 millimeter, so that is like a huge benefits from that. But of course we need to do many more experiments there. So because the validation of this, there is some other things.
Hello, sir.
Yes.
Please conclude in 5 minutes. We have 5 minutes now.
Okay, but we started late, right? So that's why.
Sorry for that.
Fine. So so I think I can conclude here. So that is the thruster application. So we did the hydrogen plasma. So hydrogen plasma almost like a that is the also we get similar type of results. But I will now go to the next part there. I will conclude here. Not much there. See, low temperature already I said. Low temperature. So low temperature, this experiment was carried out in the hydrogen plasma, or in a very high that system. So this low temperature इससे क्या होता है कि जब low temperature करते हैं तो it can aid in to produce negative hydrogen ions. तो negative hydrogen ions का जैसे आप सोचिए कि we have अभी तक के डिस्कस कर रहे थे, इलेक्ट्रॉन्स डिस्कस कर रहे थे, पॉजिटिव आयंस डिस्कस कर रहे थे, बट नाउ वी हैव ए लाइक नेगेटिव आयंस. So negative ions का क्या होता है, negative ions are utilized in a fusion reactor. सो फ्यूजन रिएक्टर, क्योंकि फ्यूजन रिएक्टर में क्या होता है, दिस इज द थर्मोन्यूक्लियर फ्यूजन रिएक्टर, तो वहां पर यू नीड सम एडिशनल हीटिंग, सो दैट वन एडिशनल हीटिंग क्या होता है कि न्यूट्रल बीम से हम लोग हीट करते हैं। सो न्यूट्रल बीम हीट करने के लिए न्यूट्रल बीम को हीट कैसे करेंगे, न्यूट्रल बीम को एक्सीलरेट कैसे करेंगे। सो इसके लिए एक्सीलरेट करने के लिए क्या होता है कि you have to have some ion beams first and after that you have to neutralize. अब न्यूट्रलाइजेशन एफिशिएंसी क्या दिखता है कि H प्लस के कंपैरेटिव टू H प्लस, H माइनस का न्यूट्रलाइजेशन एफिशिएंसी इज मच हायर एज यू कैन सी दैट। सो आप क्या करेंगे, पहले आप एक प्लाज्मा बनाएंगे, जैसे हमारे यहाँ पर नेगेटिव आयंस H माइनस बनाएंगे, ठीक है। H माइनस को यू एक्चुअली with some accelerator system, there is electrodes are there, you can accelerate making very high energy, neutralizer से pass कराएंगे, it becomes a high energetic neutral beam and that can goes to the fusion reactor and it can produce that. So क्या अभी requirement क्या है कि जो recently there is international thermonuclear reactor is there, the experiment is going on there, you have to make it that very large area H minus beam, लार्ज एरिया H माइनस बीम का जो करंट टेक्नोलॉजी वो करे RF से, इंडक्टिव RF कपलिंग से। तो वहां पर क्या होता है कि मेकिंग ए वेरी हाई करंट दैट इज टेकिंग ए वेरी हाई एनर्जी, इट इज टेकिंग द प्लाज्मा बनाने के लिए बहुत हाई एनर्जी। तो हम लोग क्या करते हैं कि वी आर ट्राइंग टू डू दैट ECR कॉन्सेप्ट वी आर यूटिलाइजिंग हियर, and the ECR से क्या होता है कि you see that even with a lesser energy we can actually produce a very high plasma density and that can produce an H minus. These are the some setup I am showing it at the next experiment here. So this is again the expansion और जो होता है कि you can see that this one is a one the real plasma picture here. That it can comes there and you can see that it was almost confined here with the magnetic field, but ये expand कर रहा है यहाँ पर जाकर uniform बन रहा है, ठीक है। So you can see that is the this is the temperature, it is cooling down there, almost like 1 electron volt is required. So around that as you go from the source it becomes cooling down there. And this one is the radial uniformity, वो पहले भी दिखाया था, यहाँ पर भी वहां पर था 25 सेंटीमीटर रेडियस मतलब, और यहाँ पर ऑलमोस्ट 35 उससे भी ज्यादा हो जाएगा, it can go to a very high there. So it becomes like a on a very larger plane you can produce a negative ions with a large area and that can later part utilized for the produce a high H minus field there. Okay, so this is some of the other experiment we have done there, because you see you have to give a like a high power there. So क्या we हमारा provision है, this is a provision है कि आप यहाँ पर there are many ports are there, उसमें you can like यहाँ पर एक source लगा है, you can make many other sources are there. So वो source लगाकर what you can do, you can distribute कर दोगे power को and therefore you can make a many plasma beam and which can actually comes down and it can produce the uniform plasma. So what you can have a high power you are injecting there, so that plasma density becomes higher there. Okay, so we had some issue with that, that is the open to research actually, that we had some issue for the maintaining very radial uniformity as to the single source compared to single source, but we are working on it. Okay, so I will conclude here. So our expanding plasma that was utilized for the different applications, we utilized for different expansion ratios. So one was that ion acceleration. So ion acceleration we have utilized to project it as a thruster. Now we utilize for argon gas. Generally, actually xenon gas is used because it's because of the high mass, so thrust will be higher there. Another is that cold electrons are produced. So that is in the argon also you can produce, but the hydrogen it becomes more beneficial because you can produce negative ions, and negative ions are one which are utilized for the fusion reactors. Okay, so I conclude here. Thank you for this opportunity. So yeah, thank you. So this is I have concluded here. Hello. Hello. Should I stop share?
Yes, sir.
Okay. Okay. Thank you. So if anything you can ask, I'm not sure that
I extremely sorry.
there was disturbance was there, but a general question you can ask also.
Actually, from the beginning, we are facing the technical issue.
But
I We
No, I
will
don't.
listen you again once we will resolve the technical issue. And I believe the audiences have enjoyed your lecture, and I really thankful to you, sir.
Okay. So if there is any general question someone may ask, there is a student.
If,
I
if anyone is having any question,
it is not. I don't know how much I can translate, because the point is that it is a little high-end research. So explaining everything is a difficult part. But I hope at least that can generate
sir,
some.
we are recording your lecture, and we will upload it on Physics on Friday website.
Thank you. That is okay. I have said that I hope that it can. It is difficult in a one go. That is a layman. It's not exactly not a popular lecture. It's difficult to understand all the things. But I hope it can at least generate some interest in the students. And you also become being a plasma background. Also, I expect that you can also do that part. Okay. So that you can encourage the students. They can, if they can pursue research in the plasma physics in future. Okay, that
Sure,
is
sure,
my,
sure.
that is what I'm saying. Okay, so anyway, that my email ID is available. So any questions also after hearing the lecture is uploaded, you can always ask me through email. No trouble there. Okay.
Any other question? Sir, audience has no question. So,
Okay.
Thank you so much, sir.
Hello.
Hello. Yes.
Hello.
Yes. Tell me.
Sir, I have two simple questions.
Yes. Yes. Tell me.
Okay, so you have mentioned plasma density.
Yes.
Okay, so how do you count this density?
Plasma density means it is not a mass density but particle density. Which means that if you take a per cc means in a like for example gas particle density. So where you are sitting here, so if you just imagine 1 centimeter by 1 cube, तो आपके वहां पर मेजर कीजिए कि how what are the number of gas molecules are there. So that is the your gas particle density. Plasma density which बोल रहे हैं, तो हम लोग बोलते हैं कि number density. So how many ions and electrons are there in that per cc centimeter cube, 1 cubic centimeter. That is
Okay,
how
sir.
we define the number density. Okay.
Okay. One thing which I have seen on your slide, that somewhere you have mentioned temperature nearly 1 lakh degree Kelvin.
Yes.
So is it possible to measure such a huge temperature?
1 lakh Kelvin, that could be like it can be possible. That's why we measure that. So it can be, if not by the probe, there are spectroscopic way to measure that. But our is like we measure, as I said, that non-thermal plasma, 10,000 Kelvin, that is there. So that can be measured by our probe there, but the electron temperature, not the ion temperature. 1 lakh Kelvin, probably it will be like a very space plasma there. That can be as a radiation measurement से हो जाएगा ना, जैसे black body radiation अगर आप measure करो तो वहाँ से temperature का concept you can get, right? That it like that. Okay. So which means the spectroscopic studies से आपको मिल सकते हैं. तो आपको मतलब जो लाइट एमिटेड कर रहा है, जैसे कि सन का टेम्परेचर भी हम लोग मेजर कर सकते हैं ना. So that also that can be done through that measurement of the radiation, like that.
sir, we will organize your another lecture in upcoming Friday.
Okay. All right.
And I will also try to resolve the technical issue which we have faced today.
All right. So no trouble. But that you organize. I mean, okay. So again, it is in plasma or some other topic.
No, on the plasma, on your research area of interest, sir.
Okay. Okay. Who is giving next class? Next.
Who is the speaker has been not decided it.
Okay.
But
Okay.
I'll let you know.
That's good. That's good. Very good. I hope that is my idea, that it should generate some interest in your students. That's it.
Yes, sir. Yes, sir.
And I thank you. Thank you. I don't know. I did not get who asked me question. I thank him. He asked me question. That is really good.
Yeah,
Okay.
sir. He is Dr. Binit Singh,
Oh, I
and
see. I see. I see.
he has completed postdoc from IIT Bangalore. Now he
Very
is
good.
working on plasmonics.
Oh, I
So
see.
he
I
is
see. That's
faculty
why
here.
it's a mature question. That's right. So anyway,
Yes, sir.
if it's come from students, that will be good. Okay. Right. All right. Thank you very much. Okay.
Okay. Thank you so much, sir. Thank you.
Okay.